Okay, in continuing with solving differential equations through using Laplace transforms, and if we cross over to a second order differential equation, and we'll say that we have, this case we have x double prime minus x prime minus 2x is equal to 0, and we have with the initial conditions, we can say we have x naught is equal to 0, and that x prime naught is equal to 2. Now, in what we have setting up along the lines of Laplace transforms, we have for that of the second order derivative of x of t. So we have s squared x of s minus s times x naught minus x prime naught. And now we have with x naught at 0, we have for this term, this will become negligible. And we have x prime naught, we have at 2. So we have for the second order derivative, the Laplace transform, we'll have s squared times the Laplace transform x of s minus 2. Now for the first order derivative term, the Laplace transform, we have s times the Laplace transform x of s minus x naught. Again, this is negligible, so we have an x prime of t. We have for the Laplace transform, we have s times the Laplace transform x of s. And for 2 times x, okay, the Laplace transform, this will be equal to 2 times the Laplace transform x of s. And for what we have with 0, okay, we have Laplace transform of 0 is equal to 0. So in the crossover, so filling in, translating what we have in the terms, going from the parametric to the Laplace transform equivalent. So we have, again, taking the expressions. Okay, so we have for the Laplace transform variable terms, if we combine and separate the other terms, so we have s squared minus s minus 2 quantity times the Laplace transform x of s is equal to 2. And here we have a trinomial that we can factor. So we have the quantity of s plus 1 times that of s minus 2 times the Laplace transform x of s is equal to 2. And then isolating the Laplace transform x of s. So we have 2 all over the quantity of s plus 1 times the quantity of s minus 2. And to fully expand, now we're going back to partial fraction decomposition of this ratio. So we have with a couple of linear factors. So we have a over s plus 1 and b over s minus 2. And looking at clearing out the fractions. So I have 2 equal to a times the quantity of s minus 2 plus b times the quantity of s plus 1. And we have a couple of zeros that we can apply. So we can solve for a if we set s to -1. So with b going out, we have -1 minus 2 is -3. And so we have -3a set equal to 2. So we have a equal to -2/3. And switching around, negating a, we can set s equal to 2 and thus solve for b. So we have 2 is equal to 3b, and we had that b is equal to 2/3. And we have with the partial fractions, okay, so you have a is at -2/3, b is at 2/3. And we have with the expanding of what we have for the Laplace transform expression x of s. So this will become -2/3 of the reciprocal of s plus 1 plus 2/3 of the reciprocal of s minus 2. And putting in terms of our function x of t, and it's going to follow now that we have for x of t, okay, we have equal to -2/3 of the inverse Laplace transform of the reciprocal of s plus 1. And we have plus 2/3 of the inverse Laplace transform of the reciprocal of s minus 2. And so we have, for the final answer, it's going to follow that we have with x of t. Okay, we have -2/3 for the inverse Laplace transform of the reciprocal of s plus 1. This being reference to e to the at power, where a in this case is going to be -1, so we have -2/3 of e to the -t. And likewise, we have 1/s-2. This is in the e to the at family, where a is at 2, so we have 2/3 of e to the 2t. And that will be the result for what we have for x of t. Okay, for what we have in the next second order differential equation, okay, we have x double prime plus x is equal to the cosine of 3t with the conditions such that x naught is equal to 1 and x prime naught is equal to 0. And just translating what we have into Laplace transform variable expressions. Okay, so here we have for the second order derivative. Okay, so we have s squared times Laplace transform x of s minus s times x naught, so we have x naught at 1, minus x prime naught, okay, which is going to be at 0. And so we have in the setup, okay, so we have s squared times the Laplace transform x of s minus s times 1, so we have minus s. And the Laplace transform of x of t, we had the Laplace transform x of s. And we have equal to the cosine of 3t, whose Laplace transform is going to be s over s squared plus 3 squared, namely s over s squared plus 9. And we have just filling in, and we have, again, second order derivative, have this combination of terms, plus x of s and cosine of 3t, Laplace transform equivalent. Again, we have s over s squared plus 9. And then we have gathering together the terms. So we have s squared plus 1 quantity times the Laplace transform x of s. And that is going to be equal to s over s squared plus 9. Now the s is going to be moved over. And if I put this as a fraction that I can combine with the first ratio, so we have s is going to translate out to, once we multiply by s squared plus 9 over itself, we have s cubed plus 9s all over s squared plus 9. And once I combine these two numerator terms with s, I'm going to have s cubed plus 10s, okay, over s squared plus 9. And we have isolating the Laplace transform variable x of s. So it come out to s cubed plus 10s all over the product of s squared plus 9 and s squared plus 1. Now, for what we have in this ratio, we're looking at breaking down in terms of partial fraction decomposition. Now, both denominator factors are quadratic in nature, okay, or quadratic in form, and you want to maintain a 1 degree difference between the denominator and numerator. Okay, so we have with s squared plus 9, okay, we have the numerator not a, but as plus b, so you have a 1 degree difference. Likewise with s squared plus 1, you have cs plus d. And looking at clearing out the fractions upon multiplying by both s squared plus 9 and s squared plus 1, so we have this rather lengthy expression. And now in terms of what we have here, the only real zero that we can apply among the s terms or factors will be from s, which we have at 0. And I'm just going to throw in arbitrarily other values of s. Now we have 4 unknowns, okay, and so we're going to apply 4 equations, okay, and so we have with our other inputs, along with s at 0, we have at 1, 2, and 3, so filling in s at 0, 1, 2, and 3, I have these equations, and now just writing where I can arrange what I have and displaying a 4x5 matrix, and we have for the first column sections, okay, we have the a coefficients, b coefficient, c, d, and the rightmost column you have the values to which we have each equation set equal. All right, so I have 0, 11, 28, and 57. Now, in looking at applying what we have in the reduced row echelon form, so you have a diagonal array of 1s and 0s. Okay, so we have, so the 1 to the left, okay, we have 1a, and that is equal to -1/8. And we have 1b, and that's going to be negligible. And then we have 0, 0, then we have the 1 in the third position, Okay, we have 1c is equal to 9/8, and then we have 0, 0, 1, 0. That signifies that d is equal to 0. Now, in taking the values of a and c, now we have, going back to the original ratio. Now again, b and d are negligible, so we're going to have only that which represents as and cs to remain. So we have a at -1/8. We have this particular ratio, we have -1/8 of s over s squared plus 9. And with c at 9/8, I have 9/8 of s over s squared plus 1. So we have, in the case of x of s, I have now -1/8 of s over s squared plus 9. And I have plus 9/8 of s over s squared plus 1. Now, if I take what I have and put in terms of the solution x of t, so I have -1/8, and I have the inverse Laplace transform, and we have of s over s squared plus 9, and I have plus 9/8 of the inverse Laplace transform of s over s squared plus 1, right, and with the sum of squares in the denominator, and with the numerators each at s, we're going to end up with cosine terms. So we have for x of t, this will come out to -1/8. What is going to be the cosine? And since 9 is the square of 3, we're going to have the cosine of 3t. And we have with the next term, we have 9/8, and this will be of the cosine of t. And that will be your final answer.